Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is loaded synchronous generators. Our objective is to examine electrically excited synchronous generators in the loaded condition. We'll explore how varying the magnitude and reactive nature of an electrical load connected to a synchronous generator can influence the generator's output, and how operators can compensate for these disturbances. This lecture is limited in scope to loaded synchronous generators in isolated conditions and does not discuss generator synchronization. We'll explore generator synchronization in greater detail in later lectures. This lecture operates under the presumption that viewers watch the unloaded electrically excited synchronous generators lecture available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please bring yourself up to speed and return when you are so qualified. In the aforementioned lecture, we examine electrically excited synchronous generators in the unloaded condition. We learned that physical construction of the stator windings influence phase shift, rotational direction of the prime mover influences phase sequence, field current strength influences voltage magnitude, and prime mover rotational speed influences both frequency and voltage magnitude. For the purpose of the aforementioned lecture, we assume the generator was isolated and not supplying any electrical load. An analogy might be installing and setting up the first generator on some small island community with no other generation facilities nor any electrical grid. Before we start supplying electricity to the grass huts, coconut farms, and fish processing facilities on this island, it's probably a good idea to establish a desired phase sequence, phase shift, frequency, and magnitude before doing so. We did so in the previous lecture by varying prime mover rotational speed, direction, and field current to achieve the desired specification. It's time to put this generator to work. In a perfect world, a perfect generator wouldn't be perturbed in the slightest by an electrical load, and output voltage would remain at the voltage magnitude and frequency no matter the magnitude of the electrical load nor its reactive nature. In the real world, electrical demand can and does influence voltage output, largely because the stator windings of a real-world electrical device are not ideal in nature, but rather full of non-ideal junk and nonlinearities that needs to be accounted for. Now, I could go ahead and be all fancy and properly model the stator windings of the generator using the Steinmetz equivalent circuit, and account for stator resistance, stator leakage reactance, rotor resistance, rotor leakage reactance, slip and magnetizing reactance, but ain't nobody got time for that. If you want this lecture done in this lifetime, let's use this far simpler equivalent circuit. Each stator winding can be modeled as a voltage source in series with a small resistance value, in series with a comparatively larger inductive reactance. The voltage source is the electromotive force produced by the generator when it's consuming the mechanical power of the prime mover. Thus far, we haven't output any electrical power, but this is where it's coming from. The small resistance value internal to the windings accounts for the real-world resistance of the coil of the wire constituting the stator winding. The comparatively larger inductive reactance value internal to the winding accounts for the inductive nature of the stator winding. An important distinction needs to be made between the electromotive force produced by the generator and the output voltage at the stator terminals. For the purposes of this simplification, let's consider just one winding of a Y-connected three-phase stator, and you're just going to have to imagine that everything is occurring in the remaining two phases with a 120-degree phase shift. Let's assume the internal stator resistive component has a magnitude of 5 ohms at an angle of 0 degrees, and the internal stator inductive component has a magnitude of 20 ohms at an angle of 90 degrees. In the previous lecture, we established 120 volts line to neutral, 208 volts line to line, 60 Hz three-phase AC. In the unloaded condition, no current flows through the internal stator resistance and inductive components, and no voltage is dropped across these components. Thus, all electromotive force voltage appears at the stator output terminals. This is essentially an open circuit scenario where all electromotive voltage appears across the terminals of an open switch. In the unloaded condition, this is the one scenario in which a generator output at the terminals of the stator is equal to the generator electromotive force, principally because with no current flowing through the non-ideal internal stator components, there is no voltage across these elements, thus no losses. In this example, in the unloaded condition, we would observe an output line to neutral voltage of 120 volts, i.e. the generator electromotive force without any losses. In the loaded condition, however, current does flow through the non-ideal internal stator resistive and inductive reactance components. Thus, these elements experience voltage drops, such that the output voltage at the terminals of the stator is different from generator electromotive force. It's perhaps easiest to demonstrate these effects of these non-ideal elements with a series of illustrated calculations. Follow along if you're up to the task. We've got 3 scenarios to discuss: resistive, inductive, and capacitive loads. This portion of the lecture presumes the viewer is familiar with series AC circuit analysis using phasor equivalents. If you're a little shaky on this subject, by all means revisit the series AC circuit analysis lecture at the Big Bad Tech channel and return when you're so qualified. Let's deal with resistive loads first. Let's first assume the electrical load in question is purely resistive in nature with a value of 1000 ohms at an angle of 0 degrees. Output voltage at the terminals of the stator is therefore voltage across the purely resistive electrical load elements. Taken in series, the inductive and resistive components internal to the stator and the purely resistive electrical load represent a total impedance of 1105.2 ohms at an angle of 1.1 degrees. An application of AC Ohm's law demonstrates 119.4 milliamperes at an angle of negative 1.1 degrees of current flows through all 3 series components. Subsequent applications of AC Ohm's law demonstrates the non-ideal resistive component internal to the stator winding experiences a voltage drop of 0.6 volts at an angle of negative 1.1 degrees. The inductive component internal to the stator winding experiences a voltage drop of 2.4 volts at an angle of 88.9 degrees, such that the purely resistive electrical load experiences the remaining 119.4 volts at an angle of negative 1.1 degrees. Concerning ourselves solely with the magnitude, in this lightly loaded condition, output voltage dropped from a theoretically possible 120 volts to a reduced real-world value of 119.4 volts. This is to be expected given all the junk in series with the purely resistive electrical load. Now let's see what happens when we decrease the magnitude of the resistive electrical load to 100 ohms at an angle of 0 degrees and draw more current. Stands to conjecture more current through the non-ideal internal stator components will result in more of a voltage drop across them, thus less output voltage at the electrical load. Let's see if this is the case. We could perform the exact same lengthy series AC circuit analysis making use of AC Ohm's law as previously, or efficiently and directly arrive at the same result using the AC voltage divider rule. An application of the AC voltage divider rule demonstrates the purely resistive electrical load experiences a reduced output voltage of 112.3 volts at an angle of negative 1.1 degrees. These calculations demonstrate a phenomenon observable in real life, that phenomenon being increased current drawn by external resistive loads results in an increased voltage reduction at the output terminals. A graph of output voltage as a function of load current for resistive loads might look something like this. In the unloaded condition, i.e. no current, output voltage was the ideal 120 volts we initially established. When we connected a 1000 ohm resistive load and draw just a little bit of current, output voltage dropped to 119.4 volts. When we connected a 100 ohm resistive load current increased and output voltage dropped to 112.3 volts. Long story short, increased current demand for resistive loads results in a reduction of output voltage. Let's now do the same thing for inductive loads. We should observe a similar phenomenon, although slightly more dramatic in nature. This time, let's assume the electrical load in question is purely inductive in nature with a value of 1000 ohms at an angle of 90 degrees. Output voltage at the terminals of the stator is again the voltage across the purely inductive electrical load. As previously, let's jump right to the answer with a quick application of the AC voltage divider rule. An application of the AC voltage divider rule demonstrates the purely inductive electrical load experiences a reduced output voltage of 117.6 volts at an angle of 0.3 degrees. Notice the drop for the inductive load is a little bit more pronounced than it was for the resistive load, even with a similar magnitude. Let's see what happens when we decrease the magnitude of the inductive electrical load to 100 ohms at an angle of positive 90 degrees and draw more current. Another application of the AC voltage divider rule demonstrates the purely inductive electrical load now experiences a reduced output voltage of 99.9 volts at an angle of 2.4 degrees. Again, notice the drop in output voltage for the inductive load is a little bit more pronounced than it was for the resistive load of the same magnitude. These calculations demonstrate a phenomenon observable in real life. That phenomenon being increased current drawn by inductive loads results in increased voltage reduction at the output. A graph of output voltage as a function of load current for inductive loads might look something like this. In the unloaded condition, i.e. no current, output voltage was the ideal 120 volts we initially established. When we connected a 1000 ohm inductive load and drew a little current, output voltage dropped to 117.6 volts. When we connected a smaller 100 ohm inductive load, current increased and output voltage dropped to 99.5 volts. Similar to resistive loads, increased current demand for inductive loads results in a reduction of output voltage, only it's more pronounced. Let's do the same thing for capacitive loads. The viewer may initially suspect similar behavior as we observe for resistive and inductive loads. However, I should remind you that capacitive and inductive elements are essentially polar opposites of one another, can counteract one another. For this reason, pay attention to a rather surprising phenomenon. Let's assume the electrical load in question is purely capacitive in nature with a value of 1000 ohms at an angle of negative 90 degrees. Output voltage at the terminals of the stator is again the voltage across the external purely capacitive electrical load. As previously, let's jump right to an answer with a quick application of the AC voltage divider rule. The AC voltage divider rule demonstrates the purely capacitive electrical load experiences an increased output voltage of 122.4 volts at an angle of negative 0.3 degrees. This is entirely opposite of the effects we observed with resistive and inductive loads, yet entirely to be expected. Note the inductive nonlinearity internal to the stator windings and the capacitive electrical load essentially work against each other, so the load experiences a higher output voltage drop. Let's see what happens when we decrease the magnitude of the capacitive electrical load to 100 ohms at an angle of negative 90 degrees. Another application of the AC voltage divider rule demonstrates the purely capacitive electrical load now experiences a further increased output voltage of 149.7 volts at an angle of negative 3.6 degrees. These calculations demonstrate a phenomenon observable in real life, that phenomenon being capacitive loads experience increased output voltage. A graph of output voltage as a function of load current for capacitive loads might look something like this. In the unloaded condition, i.e. no current, output voltage was the ideal 120 volts we initially established. When we connected a 1000 ohm capacitive load, output voltage rose to 122.4 volts. When we connected a 100 ohm capacitive load, output voltage increased to 149.7 volts. In contrast to resistive and inductive loads, increased current demand for capacitive loads results in increased output voltage.